Good afternoon. Welcome back to Advanced Modeling Methods, and we're going to continue our discussion on the method of weighted residuals, and in particular we're talking about the co-location version of the method of weighted residuals. We're going to talk about different versions, and then we're going to show how every one of these different versions turn into a technique that's well known. Okay, so we're talking about the co-location form or type of the method of weighted residual. So this is advanced modeling methods. This will be lecture 3, right? So 1D example, we're going to do an example of co-location method of weighted residuals. Okay, so the example we're going to do is again a heat conduction example, and where the governing equation is the second derivative of the temperature plus, and we're going to make it a little bit more difficult. So that the generation term, close bracket. This is generation UG triple prime over K. So now you can see that the generation term, to make the problem a little bit more difficult, we made the generation term, instead of being a constant, we made it a function of temperature and a function of position. Okay? So we have a bar that is L long, and so the bar has an internal energy generation, maybe due to an electrical resistance or some sort of reaction going on inside the material, which produces energy that's proportional to the temperature and proportional to the position as it goes in the L and the X direction. Okay, this is just again an analytical problem. It's an academic problem. It's a problem just to test the method, and the reason I want to make the problem a little bit more difficult and make the generation that way is because if we keep the problem like this and use a constant generation, what do you think the solution of this equation would be? Solution of a 1D second order equation, just like this, with a constant term here, is a parabola, right? And it will be very easy to match a parabola with whatever numerical method. Actually, we'll match it exactly. So we want an equation that will yield a solution that is not as simple as a parabola, it's a regular parabola. Everybody clear with that? Now the boundary conditions that we will use, we're going to use first kind boundary conditions on both sides. So that the temperature at x equals 0 is some T0, and the temperature at x equals L is some TL. And remember the hat I use to denote that this is a provided value, it's a given value, it's imposed. All right, so here's the geometry of the problem is pretty straightforward, although we've gone from 2D now to 1D, just to exemplify what we're doing. This is the X direction, right? This would be 0, this will be L. That's omega right there, the domain. Okay, the domain is just a 1D line, and therefore, the boundary, gamma T and gamma T, is just a point on the left and a point on the right, okay? In the 2D problem, the domain was a 2D surface or region, and the boundary was the line around that region. In a 1D problem, the domain is just a 1D line, while the boundary is just a point here and a point here. And at those locations, we're imposing temperature T0, and at this point, we're imposing temperature TL. Okay, so this is a standard heat conduction problem, and the only thing that's not standard about it is that the generation term exists and it's a function of temperature and function of position. Again, just to make it a little bit more complicated. Now, the exact solution of this problem, which you can find very easily through method of variation of parameters or indeterminate coefficients. Okay, this is a second order non-homogeneous This is second order constant coefficient equation, solutions in terms of sines and cosines, as you can see. And then you use indeterminate coefficients to determine the coefficients due to the non-homogeneous term. And it's you can readily arrive at the exact solution, d0 times the cosine of x, this will be d0, plus TL plus L minus d0 times the cosine of L divided by the sine of L times the sine of x minus x. Let me make sure this is correct, because it looks weird that we have an L adding a temperature. Should be, let me see, right, if we differentiate this twice, we'll get the same, except the x will not be there, but the negative signs, so that will go away. And if we evaluate this at x equals 0, this one will go away. I'm sorry, this one will go away at x equals 0, so we get t0. And at x equal L, okay, that would be sine of L divided by sine of L, and cosine of L, this one will go away. It will TL L minus L, yeah, that's just consistent, okay? So everything's fine. This one satisfies both the governing equation and boundary conditions. This satisfies governing equation and boundary conditions exactly. All right. Now, we have an exact solution, so we have a point of comparison. We're going to do a numerical approximation and see how close we can get to this solution. So let's try an expansion in terms of trial functions of the form summation j equal 1 to n alpha j phi j of x. Okay, and to determine the n coefficients of j's 1 through n. Okay, so that's the basis of all of these techniques. Expand the temperature or the approximation of the field variable in terms of a linear combination of coefficients and arbitrary trial functions which are selected by you. Okay. So what do we do? Define the residuals. And that would be, well, the residual over the domain is equal to the second derivative of this expansion plus this expansion plus x. Right? Because that is the governing equation. And should this be the exact solution, this residual will automatically go to 0. But we're assuming or presuming that we don't know the exact solution. And then we have a residual on the portion of the boundary where the temperature is imposed. And let's say where the temperature is imposed at x equals 0. And that would be equal to, well, is Tx minus t0 when x is equal to 0. Okay, there's no integral. There's no, since it's a Dirichlet condition, it's just the defect between the approximate solution and the imposed boundary condition. And then we have another portion of the residual on the portion of the boundary at x equal L. And that would be this approximate solution minus the temperature that is imposed at x equal L. So notice I've defined three residuals separately. And now it's time to decide whether we want this to be an interior, whether we want to use an interior method, a boundary method, or a mixed method, okay? And that would mean, okay, do we pick a solution that we force to satisfy the boundary conditions so these residuals go to 0 automatically, we don't have to minimize them, and then just worry about the interior, that would be an interior method? Or do we pick a function, t, that satisfies the governing equation somehow, right? And then we force it to satisfy so this residual goes to 0, and then try to figure out how to minimize the residuals on the boundary. That will be a boundary method. Or do we pick a temperature that doesn't satisfy anything, and then try to minimize these three residuals simultaneously? Okay. Now the usual choice is an interior method. Okay. Select or choose to use an interior method. Approach such that the approximate solution, t wiggle or squiggle, automatically satisfy the boundary conditions. And therefore, the residual on this portion of the boundary is equal to the residual on this portion of the boundary, which is equal to 0. That means that somehow the residual on this portion of the boundary, which is equal to t hat of x minus t0 at x equals 0 is equal to 0, will mean that this is the case. Somehow we have to come up with an expansion that automatically is forced to satisfy that. And it would also mean that therefore, this is the case. So let's see what we can do to be able to accomplish that. But before we worry about the only residual to minimize is this one. So how do we minimize the residual? We say, well, it's the integral over the domain of r omega times some weight functions. The omega must be equal to 0, such that omega is the x that belongs to the interval between 0 to L. That's what the domain is. So we know what the residual of the domain is. We had it up here. Right there. It's just a governing equation. And we know that since we're talking about collocation, the weight functions are again the Dirac delta functions at certain collocation points xi. So now this becomes the integral from 0 to L, that's the domain, integral from 0 to L of the residual, which is the second derivative of the approximate solution plus the approximate solution plus x times the Dirac delta function of x by xi. The x must be equal to 0. Okay, that's pretty standard. This is what we've done so far. Well, in the previous example, the equation wasn't this. The equation was just this plus u. Okay, it was the second t plus u over k. Now we're adding some complication, and we're actually going to solve this problem. All right. So now it's time to use the sifting property of the Dirac delta function. And remember, that means that if a Dirac delta function is inside an integral multiplying any other form of functions inside the integrand, it will basically mean that this integral would disappear, would just be the evaluation of this integrand at the collocation point of the Dirac delta function. So this will just simply reduce to the second t squiggle, the x squared evaluated at xi, plus t squiggle xi plus xi is equal to 0. And that is the minimization of residual form, the algebraic form. Okay, we've eliminated the integral, now it becomes an algebraic form. It just reduces to this. All right. Now, the fact that it's collocation means that the weight functions are the Dirac delta functions. Okay, this is why it's called collocation, because it means basically taking the governing equation and collocating it at arbitrary points. Okay, the integral disappears. Now, the other choice to make now is what trial functions are we going to use? We just basically said that this t squiggle is a summation of some alphas plus some trial functions that are arbitrary. Now we need to decide what to do with those. So let's see. I want to select collocation points, and those collocation points are going to be between 1, xi, xi plus 1, xi minus 1, and xn. So we have n collocation points, and we are going to assume that the distancing between the collocation points is uniform. Okay, that doesn't need to be the case, but for simplicity, that's what we're going to do right now. So we have n collocation points, xi, such that I goes from 1 to n. And so we have xi is equal to I minus 1 times L divided by n minus 1, such that delta x is equal to L divided by n minus 1. Okay, L is the total distance of the domain. If we take the number of points minus 1, we have n minus 1 segments. Each of the grid spacing is just L over n minus 1. Right? So this conforms, this is part of the algorithm that we're going to use. When I is equal to 1, x is equal to 0. When I is equal to n, x is equal to L. Just pretty straightforward. We'll do it on MathCAD. But take the note that collocation points need not be equidistant. We're just deciding to do so in this case. Notice also that collocation point x1 belongs to gamma t0, while xn belongs to gamma tl. Therefore, x2 all the way to xn minus 1 belong to omega. So these two collocation points are part of the boundary. All the interior collocation points then now are part of the domain. So that's how we are going to enforce the temperature, the approximate solution of the temperature to exactly satisfy the boundary conditions. And then how is it that we're going to enforce these equations right here? Okay. So basically, the algorithm is going to read like this. At I equal 1, x equals to x1, t of x1 will be equal to the imposed value t0. That way we automatically satisfy that condition. It's an interior problem. The residual on that portion of the boundary is 0. At I equals 2 through n minus 1, x is x2 through xn minus 1. And what we try to do is satisfy the second t, xi, dx squared plus dxi plus xi is equal to 0. And finally, at I equal n, x equals xn, t xn is equal to the imposed boundary condition on the right. So now we have exactly n equations, n simultaneous equations for the n alphas that we're trying to find. So these are n equations for n coefficients. Alpha j. All right. So what I'm going to do now is replace the trial functions in here using the expansion. So remember, the expansion was this, the same one we've been looking for from the beginning. Summation of alphas times some trial functions. So we have at I equal 1, x equal x1, then we have the summation from j equal 1 to n of alpha j phi j at x1 should be equal to t0. There's one equation that relates all of the alphas in a single equation. Second equation, or second set of equations is, well, we have n minus 2 equations. So x will go from x2 through xn minus 2. And that means that this is the second derivative with respect to x squared of, let me try to fit this in here, j equal 1 to n of alpha j phi j of xi plus the summation of j equal 1 to n alpha j of xi is equal to minus xi. So I put the xi on the right. And the last portion of the algorithm here is I equal n. That means x equal to xn. That means that the summation from j equal 1 to n alpha j phi j xn is equal to TL. Right? So we know that we can reorganize this. We can pass this derivative, because this is a linear combination, so this derivative can pass directly into the trial functions without touching alphas, just constant coefficients. So basically what will happen is that we will have, the first equation will look like alpha 1 phi 1 evaluated at x1 plus alpha 2 phi 2 evaluated at x2 plus alpha n phi n, I'm sorry, this is x1, evaluated at x1. The entire first equation is evaluated at x1. Right? The second equation is going to look like, well, I'm going to isolate the alpha. Alpha 1 times, let's see, the second derivative of phi 1 evaluated at x2 with respect to x squared, plus phi 1 evaluated at x2 plus alpha 2 times all of these again, phi 2 evaluated at x2 plus phi 2 evaluated at x2 plus alpha n times second derivative of phi n, the x squared evaluated at x2 plus phi n evaluated at x2, and that would be equal to minus x2. That's the right hand side. We will do this n minus 2 number of times to alpha 1, the second phi 1, the x squared of x of n minus 1 plus phi 1 of x of n minus 1 plus alpha 2 that multiplies the second of phi 2 the x squared over x of n minus 1 plus phi 2 over x of n minus 1 plus alpha n second of phi n the x squared over x of n minus 1 plus phi n at x of n minus 1 is equal to minus x of n minus 1. So all of these and the last equation looks like alpha 1 phi 1 xn plus alpha 2 phi 2 xn plus alpha n phi n xn is equal to TL. So as you can see, you have n simultaneous equations for the n alphas that you're trying to find. And this seems like a fully populated system where all the coefficients exist on that matrix. So you have a matrix A times a vector alpha equals a right-hand side B, where that right-hand side B contains the 0, minus x2, minus x3, all the way to minus xn minus 1, and TL. And how do you solve the system? Well, it's a linear system. You can invert the matrix, find the alphas, and problem solve. Okay? And problem solved. Because that means that the solution you're looking for, where you formulate it, you have the alphas now, and the trial functions you had already pre-selected. We haven't said anything about these trial functions yet. We can pick whatever we want, and the only constraint or requirement is that these trial functions are linearly independent of each other. That's it. We can pick whatever we want. We can pick exponentials. We don't know what the nature of the exact solution is. In this case, we know it's a sine and cosine and an x, but it's just because we know the exact solution. Normally, you wouldn't know the exact solution. So you can pick whatever fees you want, and hopefully you will get to approximate the solution. Let's see how well we do. All right.
Professor, can you bring it down just a moment?
Sure.
Could you explain again the alpha is equal to the inverse A matrix times?
Well, this is a linear system.
Okay.
This is a system of simultaneous equations, right? Right here. Although this is a system of n simultaneous equations with n unknowns, alpha 1, alpha 2, all the way to alpha n. Those are the unknowns.
Yeah.
Okay? What you would in linear systems say x1, x2, x3. Our unknowns are the alphas in this case. So we have a matrix of coefficients. This is coefficient A11, A12, all the way to A1n.
Okay.
This is coefficient A21, A22, all the way to A2n. This is coefficient A n minus 1, 1, A n minus 1, 2, all the way A. This is coefficient A n1, A n2, A n n. So that completes all the coefficients of this square matrix times a vector of alphas. This is how you multiply a matrix times a vector. It would actually turn out to be exactly like that. And the right-hand side vector B is this, T0. All of these are knowns. Okay? So how do you solve a system of equations? You use Gaussian elimination, you use Gauss-Seidel elimination, you use general minimization of residuals, by conjugate gradient method, whatever method you want, whatever method is available, the computer or MATLAB or MathCAD or any of these mathematical spreadsheets have many different techniques as to how you solve a system like this. But in essence, it all comes down to saying that alpha is equal to the inverse of A times B. That's how you solve the system. All right, well, normally solving it this way is not the most efficient way because getting the inverse of a matrix is computationally intensive. But alpha is the inverse of A times B. Whichever way you find it, it would end up being A inverse times B. All right, so the only left thing to do is selecting the trial functions, right, the fees. Now, let's choose the trial functions. Vj of x. So what do we pick? We need n independent functions. Okay, so we need n functions. Let's say, well, we Let's use one polynomial, one's an exponential, one is a logarithm, one is a sine, another one's a cosine. We can do that if we want to, but that will be too tedious, especially for bookkeeping purposes. Because what if we change n from 20 to 30? What if we decide to use 30 points, 30 collocation points? Now we need 30 functions. So what do we pick? So we need a sequence of functions that we can easily bookkeep, right? The obvious choice is always polynomials. Let's pick polynomials of different orders because automatically polynomials are nice. One, because they're not singular. Polynomials always have n differentials. They're not only non-singular, they're continuous, always. Okay, they will go to infinity at x equal infinity, and they will go to infinity at x equal minus infinity. And the other nice thing of polynomials is that they're always independent from each other if you pick different orders. So a polynomial of order 2 will always be linearly independent from a polynomial of order 1, and so on and so forth. So if we pick increasing order polynomials for the functions, then we're good. The only bad thing about polynomials is that they oscillate too much. Okay? They have a tendency to oscillate too much, so we have to be careful. If we pick polynomials and we're not careful with the scaling and so on and so forth, then we might run into oscillation problems that are unwanted. Because this solution, although it looks like a sine and a cosine, it might not oscillate because in the range between 0 and L, it might just be a smooth looking function. Okay, so let's try polynomials of increasing order such that phi j of x is equal to x to the j minus 1, right? So the first function when j is equal to 1 is 1, right? Therefore, you can see it here, phi 1 of x is equal to 1. Phi 2 of x is equal to x. Phi 3 of x is equal to x squared. So on and so forth, all the way to phi n of x equals to whatever n is minus 1. So if we decide to use 20 collocation points, we're going to have polynomials all the way to order 19. And those are guaranteed to be independent of each other. How do these polynomials look like? If you plot them, x and y, and let's say I want to plot them from 0 to 1. Polynomial 1 looks like this. This is phi 1 of x, right? It's a constant. Polynomial 2 looks like this. Polynomial 3 looks like this. Polynomial 4 looks like this, and so on and so forth. They get flatter and flatter and flatter. So somehow, we're going to build a temperature that we don't know what it looks like, supposedly, and we just have constraints, which is the governing equation and boundary conditions, that is a combination of these functions here, and somehow we're going to make up what it really looks like. So we need, not only we need the trial functions, but in the algorithm, notice, we need the second derivative of the trial function. Okay? The second derivative of phi j with respect to x squared is what? Well, we can do it in sequence. What is the second derivative of 1?
0.
0. What is the second derivative of x?
0.
The second derivative of x squared?
2.
Let's continue here. The second derivative of x cubed?
6.
6 6x, and so on and so forth. So that by the way, this is double prime, huh? Taking the second derivative. And the second derivative of the nth function would be n minus 1 times n minus 2 power xn minus 3, right? So therefore, the second derivative of phi j with respect to x squared is equal to, we have to be careful because the second derivative is j minus 1 times j minus 2 times x to the power of j minus 3. But what if j is equal to 1, for example? If j is equal to 1, the second derivative should be 0. But if you look at this, if j is equal to 1, then you're going to have x to the power minus 2. So you're going to have a rational function there. So you have to be careful that for indices less than 2, the solution must be forced to be 0. Is that clear? If j is less than 3, if j is greater or equal than 3. Is that clear? Right? If the derivative would the second derivative of phi j with respect to x is just this. It's just this form right here. But for validation purposes, we need to make sure so that to avoid a singularity, because if we just keep it like this, we might run into the problem of 0 over 0, right? When we're evaluating this function at x equals 0, and then it's j minus 1, j minus 2. Let's say at j equal 2, for example, it will be j minus 1, j minus 2, that's 1, that's 0, and x to the power of minus 1, right? So it's 0 over x, and when x is equal to 0, you get 0 over 0, and that blows up. So you don't want that to blow on your face, because you're differentiating polynomials. The differentials of polynomials are always polynomials, okay? They're never going to be rational functions. Is that confusing or, okay? All right. So that's all. Now we need to implement this in the computer. You'll see how easy it would come up. All right. So, you know when you're ready, you can move. Ready? All right. So, the PC. Never saves for no reason.
It's not ready.
Okay. Just to install MathCAD on this computer. All right, so let's do it from scratch. I already did it, but I want to do it from scratch again so that we can, on the process of learning MathCAD. So let's pick T0, and I'm going to use T.0 to use this as a subscript. And let's make that 15. Let's make T.L 25, and let's make L equal 1, okay? And the temperature, this will be the exact temperature, looks like T0 times the cosine of x plus TL plus L minus T0 times the sine of L, all of these divided by this, sorry, this would be the cosine, and all of these divided by the sine of L times the sine of x minus x. Alright, that's the exact solution. I'm going to say that x go from 0, 0.01 all the way to L. Remember, that's how you describe a range. 0, then the next element on the range, 0.01, and then semicolon. It's not dot dot, it's semicolon, L, whatever L is. Alright, so I'm going to introduce a plot. That will be shift 2. And on the x-axis I want x, and on the y-axis I want t of x. And there's the exact solution. As I mentioned, even though the exact solution is in terms of sines and cosines, well, you don't see any oscillations, at least in this range from 0 to 1. Okay? Somehow, the temperature stays within the limit. Remember, if there hadn't been any generation, if UG triple prime over K is 0, the solution of that equation is just a straight line from here to here, just plain old heat conduction, right? You have two temperatures in a conductive medium that is homogeneous, the temperature is linear, right? If you have a constant generation, then this would be a parabola, whatever that is. It will not never grow over this value. Well, it could potentially, sorry, my bad, because there's generation. So the internal energy generation might make the temperature internally larger than the boundary temperature. It's the only time that would be off when you have internal energy generation. And in this case, this is sines cosines. And the reason, again, we made it this way is because we wanted to complicate things and make sure that we can capture that solution. All right, so now let's define the collocation points. We are going to select n to be, let's say, 11 points. That means that we have 10 segments. We can change that number, and MathCAD will parametrically modify everything and get you to the solution.
You say 11 segments because we have to consider 0?
Well, 11 points. That includes the two ends. So that would mean that you have 10 spacings in between. Okay? And that's a good point. Consider 0. By default, if you go to Tools here and Worksheet Options, the origin of any array is 0. Okay? In MathCAD, the origin of arrays is like in C. 0 starts at element number 0. In Fortran, it's element number 1. So if you use MATLAB, you're used to this first array starting at 1 because MATLAB is written in Fortran. Okay? So one thing I want to do for consistency, and I do this all the time, is set this number to 1. Or instead of setting it there, I can set the label directly here. I can say origin equal to 1. And MathCAD will automatically understand that this term origin is the same as changing it in the preference dialog. Okay? Alright, so I am going to let I go from 1 through, not 11, through n. Okay? I's 1 through n. So that's the range. I don't need to specify the second number because I want a unitary step in between. I could if I want, but now delta x, D, capital D, Control G will get me to delta. X, what is delta x? Is equal to L divided by the number of segments, n minus 1, right? So L is equal to 1. If I say equal, it will tell me, well, delta x is 0.1 in this case. And this will parametrically change if I make n equal 21. This will be 0.05 and so on and so forth. Pretty straightforward. And I want to define the collocation points. And I'm going to call the collocation points xi. Even though it's x subscript I, or I'm sorry, x subindex I, I'm gonna call it xi to differentiate from this x. X is a continuous range between 0 and L. This one is just a set of discrete collocation points. So I just wanna make a difference between those two. And xi, I want to use the left bracket to indicate index. Okay? Left bracket indicates index. I, this is the index variable that I selected, is equal to I minus 1 times delta x. Right? So if I display xi, I don't have to specify the range or the index. I can call this whatever I want. I can even call it x, but then that will supersede this one and I need the two of them. But if I want to display xi, I say xi regular equal, and you see what happens. It gives me 0, 0.1, 0.2, 0.4, 3, 4, so on and so forth. Okay? Let me move this a little bit here.
So that's an array?
That's officially an array. It's not a range. See, if I print this is a range. This one defined like this is a range. So if I display x, it's a range, but it's not formally an array, so you cannot access every element of x. Okay? It's just a range between 0 and 1 in steps of 0.01. This one is an actual array. So I can actually ask, what is element number 5 of this array? 0.4. Right? There we go. So, all right, what next? I need the trial functions. The trial functions that we're going to use are phi, right? Capital F, control G. That's Greek F. And those are going to be a function of x and a function of j. Right? Well, j is a sub-index, but I cannot define an array of functions. Okay? In MathCAD, I cannot define an array of functions unless I do it manually, unless I actually insert a vector and go element by element and introduce it. So I'm just going to make j another argument in this variable. And what is this? It's x to the power of j minus 1. Is that clear? The trial function? All right. The other thing we need in the trial function is the second derivative of these. Okay? Which we said, I'm going to call it d2 of f, which is also a function of x and a function of j. And we said that that was going to be j minus 1 times j minus 2 times x to the power of minus 3. I'm sorry, j minus 3. Right? But that might create a problem, especially, see, I can say, well, what is, give me d2f at x equals 0.5, comma 2. When j is equal to 2, I should get 0, and it's fine. 0, right? Because when j is equal to 2, even though this is 1 over x, this term right here goes to 2. However, if I want to say, this might be a problem, if I want to say, well, give me that when j is equal to 0, when j is equal to 1, well, it worked out. It knows how to solve the limit. So we might not need anything after all. Okay?
What did you expect?
Well, it's a 0 over 0.
Fortran won't do it, though.
Yeah, you have to be careful. In a high-level programming language, you have to, because this evaluates to 0 over 0. Right there. See, when x, I'm sorry, not when. I'm looking at this number. See?
There.
Now I got an error. Okay, so we do have to be careful. Because at x equals 0, this is supposed to be 0, no matter what. When j is equal to 2, this, the second derivative of this function of x squared is, of x to the 1, is always supposed to be 0. At x equals 0 at any value of x. So what I'm going to do is I'm going to introduce this right here. I'm going to introduce a programming line, and I'm going to say, well, the function f is equal to 0, and it's going to be this only if J is greater than 2, right?
3.
Greater or equal than 3, or it's greater than 2, right? And add a line. Sorry. It's equal to this. Okay, and then we're going to return F. Okay, this is how you do a condition. So now, if I do it this way, I'm going to evaluate here, well, what happens with D2F at x equals 0 and j equal 2? I do get 0, because if it's being forced to be 0 through here, except when j is greater than 2 when it evaluates this way. Is that clear? This is going to be available for you to look up.
You just added the line when you did the condition, right? You said equal
Yeah.
to comma.
Yeah, line.
So if you were to insert 4, you would actually get a finite variable, or F.
What's that?
If you were to change the j value from 2 to 4,
Let's make it 5. Well, I'll still get 0 because I'm evaluating at 0. But if I evaluate at 0.1, I get whatever the second derivative of that polynomial 5, that would be 5 minus 1 times 5 minus 2 times 0.1 to the power 2. Yeah. And that's the case. It's 4 times 3 is 12. 12 times 0.01 is 0.12. Okay? All right. I need to say. I already did this. So, what else do we need to do? We need to then populate the matrix. And the matrix is going to look like, well, let's start I equal 1, and let's do j equals 1 through n, and the matrix A, I comma j, be phi of xi comma j. Right? That's the first equation. The elements that's on your notes. The elements of the first equation are simply the trial functions evaluated at each of the first collocation point. This is supposed to be I, but I is equal to 1. All the trial functions. So now the second equation goes from 2 to n minus 1. J, well, all the columns of the matrix. And I'm going to say A, I comma j is equal to, what do we have? D2F control G, xi, I, comma j, plus, B, xi, I, comma j. Right? And the last of the equations is when I is equal to n for all the columns of this matrix. Well, this one will look identical to this one. Just gonna copy here. All right. So we need to populate the right-hand side vector as well. And the right-hand side vector, we're going to say B, too high, up. Bi is equal to T0, right? First element of the right-hand side vector is T0. Second element, or the rest of the elements, C, B, I is equal to minus xi, I. And the last element goes here. Yeah. Try to line it up because remember these interprets from left to right. Okay, that's it. You want to check and display the elements of A. We should have an 11 by 11 matrix. And those are the elements of that 11 by 11 matrix. Okay, if you want to check the elements of B, Well, the first element is T0. All the other elements are the negative of the position. And the last element is 25, that's the last temperature. All right, so what do we do next? We're going to say alpha, the coefficients alpha, are simply the matrix A to the power of -1 times the vector B. That's that simple. Okay? So, if we want to display the alphas, A contra G, those are the coefficients of the expansion. So those are the coefficients that combine all these 11 polynomials, okay, that look like more flat and flat and flat functions, and somehow these are going to try to mimic what the exact solution, if we did it correctly. All right? So, we make that T, what are we going to call this? T collocation, COL, as a function of x, is equal to the summation from J1 to n of alpha index, that's left bracket, J, times phi x comma J. So now this is an actual function. It's an actual function that combines 11 polynomials of 11 different orders with 11 coefficients. And somehow, those 11 polynomials with 11 different functions and 11 different coefficients would have to look like that sine cosine function. So let's see. Let's do it down here. I'm doing Control equal to separate the pages. And I'm going to bring this one here. And I'm going to print T, and right next to it I'm going to print T. So say comma, okay, put the cursor over the entire variable, say comma, and the next one I want to print is T col, the collocation version. And let's see, hit enter, it's right on top of it. Okay, this is a qualitative comparison. Okay, it looks good. But we also need to quantify how good it is, how good it is. Okay, a qualitative comparison doesn't mean much unless you attach a number to it. Well, what's the error? Okay, we can define the error. Let's say error is equal to, let's say, the sum of the squares. It's a standard deviation, right? Let's say summation over all the collocation points of the temperature evaluated at the ith collocation point minus the collocation temperature evaluated at the ith collocation point squared. And I'm going to pre-multiply this times 1 over n. I'm going to take the square root of these, and that is the standard deviation between the two solutions. Okay? I can say equal, and the standard deviation is 10 to the minus 11, so it's pretty damn good. If I want to normalize that standard deviation, this normalized error, I can say that this is divided by, again, divided by, well, let's do TL minus T0. Okay? So the two sides, or to make it more believable, I'm going to say T at xi1. That's usually not, so what I want to do is divide by the whole range of temperatures, okay? So that we can normalize it. But sometimes the larger and the smaller temperatures don't necessarily occur on the edges. But we're going to assume that that's the case in here. The xi1 n minus t of xi1 xi going to put absolute value bars over these, so we always get a positive number. So when it's normalized, you get 10 to the 12th. I can even go into these placeholder right here and put percentage. I want a percentage error. And I'm looking at 10 to the minus 10%. That's the overall error, normalized error of the numerical solution with respect to the exact solution. Right? So whatever we did was pretty good. Let's see what happens when, for example, we decide to change this n to, let's use less points, only 5 points. So we should expect a solution that's less accurate, right? If we use only 5 points, the approximation should be less accurate, and actually it doesn't look like it's any. So let me recalculate this. Sometimes it's not updated. It's still 10 to the minus 3%. So we're still in the normalized error of 10 to the minus 5. If I use 4 points, let's use 3 points. One in the mid, one at the beginning, one in the center, one at the end. That's the minimum you can do, right? So we're basically approximating the solution with a parabola. If you use 3 points, the trial functions are going to be 1, x, and x squared. So you're basically approximating the sines and cosines with a parabola. How well do we do? Well, now we start noticing some deviations, but it's still very, very close. And if I update this, now I'm at 0.4%, which is still acceptable numerically, but you can see how good the solution can get. If I do, I'm going to go to 21 points. You don't even notice the difference in calculations, even though you're inverting a matrix and so on. A 21 by 21 matrix is done immediately. But when you go to 2D and when you go to 3D, that can actually happen in a significant amount of time, so we have to be careful with efficiency. All right, so qualitatively it looks great. Quantitatively, see, now the error went up. From 11 points to 21 points, the error went up. How do we explain that? So now the error, see, the error was coming down. When it got to 11 points, it went to 10 to the minus 10. And now the error is 10 to the minus 2% when we have 21 points. Because now we have 21 polynomials. We have polynomials all the way to order 20. What's going to happen to a polynomial order 20? It's going to tend to oscillate. So we're taking a polynomial of order 12 and we're trying to ground it so it doesn't oscillate. Okay, we're trying to ground it here, and try to force it. And we also have round-off error. So a round-off means that we're trying to evaluate a function that is x to the power 20, right? And we're evaluating at 0.1, 0.2, 0.3. We're evaluating at every one of these points. So that would induce round-off error, so computational error. And that will be more apparent if I put this, let's say 101 points. Okay, if I do 101 points, look at the solution. Even though we're technically forcing the solution to be exact here and to be exact here, we're only allowing residual in the interior. This is an interior method that we use, where technically the solution that we found was perfect here. The residual, the round-off error, ate that up and made it erroneous. Okay? So that's the type of things that we need to be careful when dealing with computers, that the computer is not perfect. So if we update this, now we're at 6.6%. Obviously that solution is not correct. Any questions? All right, so when we get back next week, we'll look at another version of the collocation method of weighted residuals that doesn't suffer from that much roundup, so we can actually look at adding points, and the solution will always get better. And that's what we want. We want a method that, well, the more costly it is, the more points we add, we expect a solution, we expect a trade-off. In return, we should expect a better solution. All right, so I'll see you on Tuesday. Change this to 1. Hey. ¿Tienes clase aquí? ¿Tienes clase de qué? pasa que II. Sí. Tengo que parar la grabación.